Okay, so in this video, I'm going to go over how to do some hydroelectric calculations. Okay, so when you're done with this lesson and the associated exercises, you should be able to basically calculate the energy and power of any flowing water given certain characteristics like how high it is in the air, how fast it's flowing, um, the efficiency of a turbine, and so forth. Okay, so you can read through these. Also some key terms that we haven't gone over yet, head and head loss. Okay, so I mean, most of you probably have stood near a waterfall, or at least even a small one. But if you've ever stood next to a waterfall, you know that there's a lot of power in there. And you can actually physically feel that, feel the power. And what you really feel there is it's really the kinetic energy of the water, okay? And the related power. So there's power in the water, right? But how much is there? This is really important. Obviously, this is a fundamental consideration for hydroelectricity. So how much is there? Well, let's think about this. So think about first, what factors do you think contribute to the power and energy available in a waterfall? So go ahead and press pause and kind of think about this for a second if you'd like to. Okay, so as it turns out, there's really a couple of factors. You have how high is it? I mean, the higher it is, right, the more velocity it should have by the time it reaches the bottom. Gravity, of course, the force of gravity. This is effectively a constant. We'll consider it as a constant. What about the weight of the water? This is really, really important. Anything, a heavier object, all else being equal, is going to have more kinetic energy when it's moving at the same velocity. So the mass or the weight of the water is really important. But also the amount. So we'll look at something called discharge, which is basically, the flow or gallons per minute or cubic meters per second or whatever. But the amount is really important. You think of like a giant waterfall like a Niagara Falls versus something that you see, like you're seeing here with this relatively small waterfall. Okay, so that's also very important. Before we move forward, I want to bring this to your attention because to me this is an astounding property of water. So how much, let's put it this way, the density of water, how much does a cubic meter of water weigh? So go ahead and think about that. Think about it like a 3.3 feet cube of water. I mean, you could wrap your arms around it basically. How much do you think that weighs? Well, as it turns out, it actually is a metric ton, which is it's 1,000 kilograms, or it's over 2,000 pounds. So a ton of water in only a 3.3 foot cube. I mean, water is very heavy. It's very dense. So you can imagine if you have just a little 3.3 block of water falling from height, by the time it reaches the ground, it's going to have a lot of energy. It's going to be very powerful. And that's one of the benefits of hydroelectricity is that water has a lot of kinetic energy by virtue of having so much mass. Okay, so one of the fundamental equations we're going to go over here is the gravitational potential energy of water. Okay, so here's a basic equation we have. So we have potential energy. Well, let's look at the factors here. Potential energy, which is going to be measured in joules. This is our SI unit of energy, is joules. Is M, which is mass in kilograms. G is the gravitational constant, 9.8 meters per second squared. Then height. H is height, which is also known as head, and that is going to be in meters. Remember, we are using all SI units. Keep it SI here, folks. So we have joules is SI, kilograms is SI, meters per second squared SI, and then meters SI. Really important that we keep track of that. Okay, very simple equation, so let's go through a sample problem. Oh, by the way, if we want to convert to kilowatt hours, 3.6 times 10 to the 6 joules in 1 kilowatt hour. Okay, now let's do a sample problem. All right, so using this equation above, how much potential energy in kilowatt hours is there in 1,000 kilograms of water? That is 1 kilometer in the air. So these should be pretty easy numbers. So let's go through the calculation. Feel free. In fact, I encourage you to do this on your own right now. So let's go through this calculation. Okay, so our equation is straightforward. Potential energy is mgh. So this one is not too bad. So we have a mass is 1,000 kilograms. So 1,000 kilograms times the force of gravity is 9.8 meters per second squared times the height is 1 kilometer, which is going to be equal to 1,000 meters. Hopefully that's not groundbreaking information, and that gives us 9.8 times 10 to the 6th joules if you multiply that out. So now we remember, pay attention here, we need to go to kilowatt hours. So we insert our conversion factor, so 3.6 times 10 to the 6th joules in a kilowatt hour. And all that results in about 2.72 kilowatt hours. Okay, so this is our potential energy of just 1,000 kilograms of water, so a metric ton. So if you just have a metric ton at the top of whatever, that's a kilometer high. If that 1,000 kilograms of water falls to the ground, and it would have a kinetic energy if all of the potential energy were converted to kinetic energy, which it would be some loss. So all of that would be 2.72 kilowatt hours. So if you could harness all of that kinetic energy, you would have 2.72 kilowatt hours. So this isn't necessarily a practical problem, but it does give you the potential, so the theoretical potential. So this is the maximum possible amount of energy we could extract, and this is all hypothetically because you can never extract 100%. But as you'll see, hydroelectricity is actually pretty efficient. Anyway, that gives you the kind of your upper bound for how much energy you could get from this amount of water. Okay, now if we want to look at power, right? So this is power. Notice power available in the in water that's at height. So water that's flowing over, you know, something at height, whether it's a waterfall will be the most common example. So here's our basic equation. So P is going to be power in watts, all right? So P is power in watts, nothing controversial there. And then this is just mass per unit time, okay? So you can see this is kilograms per second is going to be our SI unit. This is also called discharge, which is actually symbolized as Q. So the SI unit is kilograms per second. You will very rarely actually have kilograms per second given. So you could have cubic meters per year, which you then can convert cubic meters per second, which then you can convert to kilograms per second with the simple conversion of density. Maybe it's going to be given in cubic meters per second, and then you know how many kilograms per cubic meter are based on that conversion, the density of water, right? And then that'll give you kilograms per second. So at any rate, you have to end up with kilograms per second if you're going to do this calculation. G is the force of gravity, H is height or head, okay, in meters. All right, so remember, this is power. So think about how this ends up as power in watts. So remember, this should look very familiar. This is very close to our equation. So remember, our potential energy equation is just mgh, and this is mgh per unit time. So really, it's just mgh per time. If you remember, our mgh is equal to joules, and if we have time in seconds, a joule per second, you probably know, is equal to a watt. Okay, so 1 watt is 1 joule per second. So really, I mean, all these units work out, okay? All right, so let's go over a sample problem. So here's Niagara Falls. These are accurate statistics. Niagara Falls is 167 feet high and has an average discharge of 2,400 cubic meters per second. What's the total power of the falls? So go ahead and press pause to see if you can figure this out, and then I'll do it for you, okay? All right, so let's go ahead and work through this. So we have Niagara Falls is 167 feet high. Okay, so we need M mass per unit time times G times H. Okay, so in this case, you have to do a little bit of unit conversion. So first of all, our mass, let's start with mass per unit time. So we know that we have a discharge of 2,400 cubic meters per second. Okay, so remember, we need kilograms per second. So if you remember our density conversion factor, there is 1,000 kilograms in a meter cubed. Do a little cross out. So that gives us 0.00000. Okay, and this is going to be in kilograms per second. Okay, that's a good start. Now we need our height. So height is 167 feet. Now if you can look up the conversion factor, we know there's about 3.28 feet in 1 meter. So we do that conversion, we get 50.9 meters. Okay, so there's a height, and there's our discharge. All right, so now we're just going to plug this in. We have our equation from here. Let's actually do it up here. So it's going to be 2,400,000 kilograms per second times 9.8 meters per second squared times 50.9 meters, and that all, sorry, it's going to give us 1.2 times 10 to the 9th watts, which is 1.2 gigawatts, okay? So this is the absolute maximum upper limit of power available in Niagara Falls given these specifics, okay? So that's power. Now, if we want to have, determine the power in a hydroelectric turbine, so a hydroelectric setup, which is a more practical problem. So this is how you would actually design a turbine. There's some other considerations, but for our purposes, we'll stick with this sort of basic. So if we want to know the power that we're going to get out of our turbine, okay, so you can see this on the right, you see a turbine here with a certain, right, so we have a certain amount of head. This would be a diversion, right, so this is a microhydro system. Diversion, this is going to be your penstock at a slope, and then you have your powerhouse generator down here and everything, okay? So if we want to know, a little more practically speaking, what the amount of power we're going to get out of this, given a certain amount of flow, we need to know the head, okay? So the head is the height. We need to know the flow, which is your discharge, and gravity. Now the thing we're adding here is efficiency, because again, nothing's 100% efficient. As it turns out, turbines are actually pretty efficient. So the equation here, the symbol is H, capital Q, gravity, and this is eta, which is just the generic symbol for efficiency. It's Greek and basically. Okay, so here's our equation, and here are the variables. So power is given in watts, SI unit, height in meters, nothing height or head in meters. Flow is discharge. Now this is a little bit different. In this case, it's going to be liters per second. And how this works is, if you look this up, okay, so sorry about that, get this to work. So 1 liter actually has a mass of 1 kilogram. So that's how that works out. So you can do liters per second or kilograms per second, however you want to do it. Okay, G, of course, is our force of gravity. Now, eta is efficiency of the system. Okay, so this is just going to be in decimal. It's unitless, okay, like, 50%, right? So 50% equals 0.5 and so on. Now, this is the efficiency of the entire system, so we have to take into consideration a few things here. This includes the turbine efficiency, but also, let me help you out here. Do one of these, okay? But also what's called head loss, okay? Head loss, and head loss is the reduction in flow due to friction in the penstock. So no matter what happens, you're going to lose some of the friction. When you do a calculation, which we're not going to do when you're designing a system, you actually have to look at like basically the size of your penstock. So if you're using, let's say, a microhydro system like a 4-inch PVC versus a 2-inch PVC or whatever, you have to look at the size or the diameter. You look at how long it is, and you also have to look at how many twists and turns or elbows you put in it. Okay, so, but anyway, we're just, for our purposes, we're going to assume a certain number. So the total efficiency is actually a combination of the efficiency of the turbine, which it turns out are really quite efficient. A reasonably good, even a microhydro turbine is going to be on the order of 85–90% efficient. So it's really good. And then head loss really depends, but if you optimize your system, you design it properly, you have a pretty low head loss, 5 to 15% maybe. Okay. All right, so let's just do a little example here. Looking at this illustration, if the stream as a discharge is 50 gallons per minute, the head is 100 meters, the turbine is 80% efficient, and the head loss is 10%, what is the power output? Okay, so this is actually a very practical problem. If you're designing a system, there are various ways you can measure the discharge, and then you measure the height through however you do that. Turbine is rated at a certain efficiency, and the head loss, you do a calculation, which is actually not too bad. Okay, so under these circumstances, what's our power output? Okay, so let's go ahead, see if you can figure that out. Go ahead and press pause, and then I'll go through the answer. Okay, so here we go. So we have, here's our set of specifics, characteristics. All right, so first of all, let's figure out, so we know our head, let's figure out our discharge. So discharge, in this case, is given as 50 gallons per minute. So if you look up, there's a conversion factor. So 1 gallon per minute, as it turns out, 1 GPM in terms of liters per second is 0.06309 liters per second or kilograms per second. All right, so a simple conversion here. So we have 1 GPM is equal to 0.06309 liters per second. Okay, and then we end up with 3.1545 liters per second. All right, so that's our discharge. All right, now what else do we have here? We know the force of gravity. Okay, so our efficiency is going to be, in this case, it's actually pretty easy if you have multiple efficiency numbers. Our overall efficiency is going to be 80% or 0.8 times a head loss of 10%. So 10% loss equals 90% efficiency, right? Hopefully that's makes sense. So 90% efficiency is a factor of 0.9. So the overall efficiency, the net efficiency, is just 0.8 times 0.9, which just gives us 0.72. Okay, so that's overall efficiency. Now we have our factors we can plug in. So power equals, we have meters, 100 meters, 100 meters times discharge of 0.06309 liters per second times gravity, 9.8 meters per second squared, times our efficiency is 0.72, and that has no dimension, and that's going to give us 2225 watts, which is 2.225 kilowatts under these conditions. Okay, so given all of the specs, that's what our power output is going to be. This is going to vary, of course, because we don't always have the exact same discharge. The efficiency might change and so forth. Okay, all right, one last one. There's also power in flowing water. I mean, if you ever stood in a stream, or even you've thrown something in a river or a stream, you know that the stream is very powerful. It can move a lot. Again, you have this velocity and you have a very massive amount of water. I mean, again, about a 3-foot cube of water weighs over a ton. Okay, so there is an equation for this as well, and here's the equation. P equals 1/2 rho AV cubed. If you have gone through the wind lesson, this equation should look very familiar. This is the same thing as our wind power equation. Wind is a fluid, water is a fluid, so you can actually calculate the power in any moving fluid if you know these factors. So you need to know the density of that fluid. In this case, it's water. Area is the cross-sectional area of flow. Right, so if you have, if you have your little turbine here, right, and this is a very generic, bad drawing. So for our turbine, this is our area. So the area of that circle, there's the water flowing past the turbine. So the amount of power in that flow of water is based on the area of a circle. Okay, and then just take the velocity cubed, of course. Kilograms per cubic meters, our density, cross-section area. Sorry, this is meters squared, and then velocity in meters per second. Okay, so let's do a calculation. If water is flowing at a speed of 25 miles per hour across the 50% efficient turbine that's 50 square meters in area, how much power is it generating? So go ahead and press pause and see if you can figure this out. Okay, so let's do the calculation here. This, again, should not be terribly difficult given that you've done a lot of this with the wind. So first, let's calculate our, so we know the density, okay, we know the density of water. The area we're given, so let's calculate the velocity. So velocity is given as 25 miles per hour, and then our factor, if you look it up, is that 1 mile per hour is equal to 0.444704 meters per second. So if you calculate that out, we're looking at about, we'll call it 11.2 meters per second. Okay, so that's our velocity. I believe we're good. So power then is 1/2 times the density of water, which is 1,000 kilograms per cubic meter, which we know from before, times our cross-sectional area, which is given as 50 square meters, times our velocity, 11.2 meters per second, and we're cubing that whole thing, multiply that out, and you get, oh, and sorry, let's do the times the efficiency, right? So 0.5 is our efficiency, so we're getting half of that out. Okay, so if we include that, we get 1.74 times 10 to the 7th. Remember, this is going to be in watts, so we can convert that to 17.4 times 10 to the 6th watts, which is 17.4 megawatts. And there, dear friends, is your answer. Okay, so given all these specs, it's going to be 17.4 megawatts of power. And again, this assumes a 50% efficient turbine. Okay, and that's it for this lesson.